Hello, everybody. This is Professor Ma, and this is the lecture's introduction to inequalities, intervals, distance, comparison statements. So we're going to change the stage come a little bit. Okay. Let me start off by review what the real line. That is, we associate each number with a position on the lines and looks like this. And basically, it's a generalizations of a ruler. A ruler usually we measure pointing in directions, starting with zeros and pointing in that directions. If I point in that direction, that's the positive direction. In other words, the direction the ruler points at is the positive direction. If I point upward, then it will be positive, going up. But horizontal rulers are extended. Imagine I have an infinite ruler go on both sides, and this double-sided ruler is the real line. So every point has its position, 2/3, 2.5, pi and minus pi, etc. This setup state we'll call that the real line. And on this real line, we define this who's bigger, who's smaller by positions, which of course corresponds to our intuition that 2 is bigger than 1. We say everything on the right is bigger than anything on the left. Okay, from comparing two things. And so, so we'll put this alligator inequality and the big ends for the big number, the pointy end for the small number. And if I write it like that, so the directions fits these directions on the line position. I always say this is the natural way of writing. It's easier to imagine that as a positions. And if I the other way, of course, I can write it the other way around, with the sign coming around. But they both say the same thing. Now, this inequality translate to everyday statements. We will call them comparison statements. They some sort of adjectives. For instance, all these statements are really inequal. They are inequality when you translate it when you translate the sentence that has descriptions, has these descriptions, you can translate that into inequalities, positive. And then you translate the picture x is bigger than 0, okay? So this is the symbol for being positive. So when mathematicians or read a sentence or blah, 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 something is positive, then immediately they translate it into this symbol, x bigger than 0, or 0 less than x. Negative. And so the phrase temperature T is positive is translated into the mathematical symbol 0 inequality less than 2. Non-positive, non-negative, those just means one more point. Okay, so I'm going to scan through these and you can think about all the sentence structures at most, at least. No smaller, no bigger. At least the same as no less than. And then you can have compound statements. Something more than something, x is more than a, but no more than b. Implicitly, when we say in this situation, implicitly we're saying b is more than a, and that x has to be in between a and b. In order to have in between, the comparison, if x is more than a and no more than b, so implicitly remain big is originally bigger than that. If it's not, then we don't get anything. So that is very important. X is more than 2, but no more than 0. if I were to state in this sentence, and that will be there will be no such number. So in order for this sentence to have solutions, the underlying assumption is the number A is smaller than the number B in the sentence structures. So we will write our statements into this inequality, and this is the pictures. So I have the sentence, the inequalities, and the interval, and that will have the picture. That will have these interval notations, and the parentheses, the A smaller number on the left, number on the left is smaller, B is bigger, and A is not in it, so I use a round parentheses. B is included, we use a bracket. So these we call interval notation. So here is an example of interval. And here are all the different descriptions and cases in interval notations, in inequalities, in brackets and parentheses. And if the number keeps going on without stopping, then we use this infinity sign, meaning keeps going, don't stop. It doesn't mean infinity. There's a signpost at infinity. You're at infinity. No. The infinity means a process. Infinity means keeps going. So it's not a number. What do we do with it? One thing we can do with these of these interval sets is we can do intersections and unions. What are intersections and unions? Let me start out with something simple. Let's suppose I have a grocery list. Okay, here's Frank's list. Apple, banana, carrot. Okay, so make it easier. A, B, C. Okay, and here's Mary's list. Banana, carrot, A, B, C, A, B, C, D, donut. There we go. B, C, D. Okay, and so we're going to go to grocery stores, and we have a lot of money, no problem. So I buy mine, and I have enough money to buy mine, and I have enough money. So now somebody's going to grocery stores, and we want to merge these two lists so everybody gets what they want. So then we will have A, B, C, D. We merge the grocery list. Okay. So this is the union of the two lists. So if I call this set A, call this set B, this is A union B, the merge of the two lists. Suppose we don't have enough money, and that the items in A is what I want, the items in B is what Mary wants, and we don't have enough money, so then of course then what we buy is we buy the things we both want, and the things we both want is B and C. We forego one the things not, and that is called the intersection. So A intersection is the common items in both lists. The overlap. Okay. So this is what union and intersections are supposed what they are supposed they are. And what we are going to do is we are going to do this instead of doing with 3 items, 4 items. We're going to do with infinite many numbers of intervals. Okay, all the numbers between 1 and 3, all the numbers between 2 and 4. Okay. So now I have different sets to play with, and so the intersections is common for things will be these, and the union will be the merge of the two. And so you'll be, and this exercise can go through examples. Okay. And one of the, for instance, one of the applications for these, simple applications, just with two sets. Let's go back to homework exercise, for example. Scheduling. You know, somebody work from 1 to 3, 5 to 6, 3 to 8. 3 different people, or here's 2 different people. When is all 3 people on the floor? When's all both people on the floor? When's one of them on the floor, but not the other? And all these are these intersections and union. And question number 12 is just very straightforward with two sets, two intervals. But you can easily imagine with like many people with many different schedules and overlapping, the union, the intersections. And it's a very practical problem. Then we come to the next topic is the absolute value. When we are on the line, here's 5, here's 2. If I want to know the distance, here's a right-hand number, here's left-hand number. If I want to know the distance between them, it's always the right minus the left, because that's how you get a positive answer. So the distance is always positive. So the distance, so the emphasis over here positive. But what happens if you subtract the other way around? Of course, you will get a negative number. And what about an well, I want to twist it around. So I don't want negative, distance is positive. Hence, the way math one way to solve this is I slap these things I call absolute value. That means whatever you get, you turn into a positive number. Okay. In particular, then the first one we have absolute value of 3, and the second one we have absolute value of what? Minus 3, right? And the goal is just make them the same answer, come out to be positive 3. In the case of 3, no problem, because it's positive, I just take as is. Just take it out of the absolute value side. Hence, the rule is if x is positive, bigger than 0, the absolute value of x will be just itself. But for the negative ones, but if I spot what's absolute valued is a negative number, then we say, oh, make it positive. How do I make a next number positive? Well, I throw in another extra negative sign on there. So, in other words, if the number you observe, if x is negative, then the absolute value, you have to give another minus number in order so you obtain the positive answer, minus x, which is a positive. So this actually the algebraic definition. But x minus y is the distance between x and y. Always positive. Positive. So this, in particular, okay, let me go up here. In particular, absolute value of x is absolute value of x 0. So it's also the distance between x and so. And so from here, we will interpret absolute value as distance and translate the distance questions into the sign and the pictures. Okay, so x less than 7, absolute value, so it looks like this. 7 to either side. In fact, this is the this is the picture for translating the phrase absolute value x minus 2 first into English or whatever your natural language is. That's the, the distance between your point and the house number 2. It has to be less than 3, within 3. It couldn't be too far off. So it has to be within this boundary of 2. You go to the right from 2, 3 up, and go from the center to go to 3 down, and that's all the axes. This is a circle in, we say this is a one-dimensional circle. Because imagine, in two-dimensional circle, that everything will be shown a big round ball. But no. This is you only have line to work with, so equal distance to either side. So this is all the circle within it. Well, I guess technically, and the circle is exact those just 2 points. This is the circle, consists of 2 points, and all these things are within that circle. Online. Okay, and then this is the 2-piece versions, and you can read these, and it's if you understand, yeah. This is the flag, the 2-piece. How we notate a flag, and how do we extract the solutions of statements of bigger than equal to something in inequality. Okay, so this is the yes, these sections, and have a good day, and bye bye.